In this lecture on bioseparations, we talk about another major process that's used for separation of biological materials, and that's electrophoresis. There's a lot of different types of electrophoresis. Electrophoresis is covered in chapters 10 and 11 of the textbook. Chapter 10 talks about the models for electrophoresis, how it actually works, and in chapter 11 we talk about the differences of different types of electrophoresis. There are multiple ways to run electrophoretic separations. But in this lecture we're going to talk more about how electrophoresis works. People tend not to understand this. They think of electrophoresis a lot like chromatography. It's not. It's actually the inverse of chromatography. And we'll discuss that in a second. Okay, you can find the links to get the textbook at bioseparationstext.com. I encourage you to buy it. It goes into a lot more detail, shows the derivations of a lot of the models that we use here, and it expands a lot in how these apply to different types of bioseparations. All right, so electrophoresis is actually an electric circuit. There's since it's a circuit, it goes in a circle. You can start pretty much anywhere and go around the circle. So let's start at the cathode. That's the positive pole, and there has to be a power supply that drives the electrical potential between the cathode and the anode, which is the negative pole. And at the cathode, the electrode picks up two electrons, and it typically picks these up from water, or more importantly from hydroxide ion, and it produces a molecule from two hydroxide ions. It pulls that electron off, that extra electron off, forces those two to combine together to become gaseous oxygen. In that process, it produces two protons. So the pH is lower at the cathode. Now those protons can equilibrate with both acids and bases. Okay, now I said usually water is the electrolyte that is interacting with the cathode and the anode. That's the dominant component in the mixture. We're typically running in an aqueous system, but there's no reason it has to be an aqueous system. We can use anything that the cathode and the anode are able to oxidize and reduce. Okay, any molecule they're able to oxidize and reduce can provide electrodes at the cathode and take up electrodes at the anode. Okay, water is a very good one. If we try to use a different solvent system, we have to make sure that the solvent system is capable of donating and accepting protons, but we can use other systems to make this work. Now, the other challenge here is the electrolyte itself should be non-conducting. Okay, it's the charged elements that we put into the mixture that provide the conduction. It's the buffer ions and the analyte that are in the mixture that actually transport charge around and complete the circuit. Okay, so there's a current that's associated with the movement of ions in that electrophoretic channel. All right, so we've got these excess protons being produced at the cathode. They can jump onto a base, ionize the base as a positive charge, and if you note, the electric field here goes from plus to minus. Well, a positive charge is going to be attracted to the anode. A negative charge is going to be repelled from the cathode, okay, and it will want to go towards the anode. So in this process, we charge up a neutral molecule. That neutral molecule then can move down the capillary, okay, or move down the electrophoretic channel, and it can give up a proton at the anode and become net neutral again. So when it does that, the proton accepts an electron from the anode, and we get two of those together. We get two electrons jump on, and we produce hydrogen. So when electrical circuits run in an aqueous system, we're always producing oxygen and hydrogen gases. This is how we separate gases, okay, and produce hydrogen from seawater. Now, at this anode, we might have a acid group, okay, and the acid group can also donate a proton to become negatively charged. So that's our A negative charge here, and that of course is going to be attracted to the cathode. So it will migrate down to the cathode, and it may pick up a hydrogen from the cathode to become net neutral, in which case it now just diffuses around, okay, as long as it's net neutral. But it's also carrying an electron with it. Now, even if these aren't reduced or oxidized at the cathode and the anode, the acid and the base can actually equilibrate with water, assuming that our matrix, that our electrophoretic matrix is water. It can share proton, it can pull protons off of water. It can, the acid can, the base can donate protons to water to produce hydronium ions, which, so there's this constant interchange that's going on, and that interchange is very important to model. It's a very rapid process. Proton exchange is a very rapid process compared to the overall movement of ions in the electrophoretic channel. This is the challenge in actually modeling or solving the models for electrophoresis. Okay, so the circuit is really completed by ion flow through the stationary phase. The electric field potential, in other words, the voltage gradient divided by the between anode and cathode, divided by the length of the electrophoretic channel, that's the electric field potential, is what drives ion movement through a stationary mobile phase. Okay, electrophoresis differs from chromatography in that the mobile phase doesn't move. That's not entirely true, we'll talk about that in a minute, but it effectively doesn't move. What moves are ionized molecules, okay, and that's typically the molecules we want to separate, whether it's small molecules or proteins, doesn't matter. They become ionized and they move according to their ionization in the electric field. And that's inherently different from chromatography, where the mobile phase moves and the ions interchange with the surface to become stationary part of the time, while the mobile phase moves on, and then they can pop back off and go back into the mobile phase. So that's the fundamental difference between electrophoresis and chromatography. All right, so let's look at an electrophoretic model. Let's simplify our schematic here. We have an ion flux of any given ions. That's I would be the ion that we're looking at. There's always multiple ions. Because of electroneutrality, there have to be at least one positive and one negative ion present. If the aqueous solution is there, there will also be positive and negative ions associated with hydronium and hydroxyl ions. So there's pretty much always 2 to 4 ions present in the system. More often than not, there are multiples. There's hundreds of ions. All right. So we apply a field to this, and we can look at a shell balance across the cross section of the electrophoretic flow channel. We have a flux of ions coming in, a flux of ions going out of that shell, that delta X shell. The length of the electrophoretic channel goes from 0 to L, and there's a concentration of ions at any given point. Okay, so these are the variables that we have. Now, we have to also consider there's a rate of ion generation or destruction in every position. Remember, there's interchange of protons. Okay, in the ionization lecture, we talk about how that interchange occurs. There's a rapid interchange of protons. It's always going on. In any aqueous system, it can be slowed down in non-aqueous systems, but in aqueous systems, it's always going on. It's very, very rapid. Okay, and we have to model that. If there's a pH change because of this ionization, that will cause a change in the ionization state. And remember, only ions move. So if we end up with a net neutral, so we have an HA that's generated by accepting a proton from the water, that doesn't move. That just sits there until it reionizes. So net neutrals, whether it's an net neutral acid or a net neutral base, those don't move. It's only the fraction that's the fractional ionization that moves. So we have to worry about that generation term. So we're either generating a positive charge or a negative charge, or multiple positive charges and multiple negative charges. All right, so the model is fairly simple. We have the change in concentration at any position for that component is equal to the flux of that component in our into and out of the delta X shell, plus any chemical ionization to that ion that's occurring. That's it. That's the model. Okay, now we have to describe that flux. Well, the flux actually has two components. If we have a concentration gradient, okay, that's the second term over here. If we have a concentration gradient, there's a diffusivity that's associated with that. So we can get axial and radial diffusion of these components in the system. But there's another driving force, and that other driving force is the voltage gradient. Okay, and there's something called the electrophoretic mobility of an ion. That's how fast it can be driven through the solution per volt of field. Okay, of field strength. That's the electrophoretic mobility. We'll talk about that more in a second. And its concentration and its charge. The higher the charge, the faster it will move for a given molecular size. The electrophoretic mobility is like diffusivity in that it scales with the size of the molecule. Okay, so we have these two driving forces, so it's a little different than just Fick's law, and this is essentially equivalent to the advective flow term that we used in chromatography. This is the electrophoretic equivalent of that. It's a driving force for the separation. Einstein related the diffusivity of a molecule to its electrophoretic mobility, and the diffusivity is equal to the ideal gas constant times the absolute temperature divided by Faraday's constant times the electrophoretic mobility. So these two things are related to one another. Lower diffusion means lower electrophoretic mobility. And it makes sense, okay, if you think about the molecule. If a molecule can diffuse faster, it's a smaller molecule, it will also have a higher mobility because it's trying, in both cases, the molecule is trying to move through a stationary fluid. One case is based on its charge within a field, in the other case is just based on a concentration gradient. So these two things are really related, and we can now make that substitution into our model, and we still have our time-dependent term. We now have our flux. Okay, we've substituted for diffusivity. We have our diffusive flux times the electrophoretic mobility, and we have our voltage-driven flux, or our field strength-driven flux, times the electrophoretic mobility. Okay, and then we have our rate of generation. I haven't dealt with the rate of generation yet, and I'll talk a little bit about that in a minute. Now, there's a few other ancillary things that we have to worry about. One is the electric current. The electrophoretic flow channel is effectively a resistor. There's a resistance to the movement of the ions, which is related to the ability of the ion to diffuse through the matrix. There's a drag on the ion as it's moving through a stationary fluid, and that drag translates into a electric, or that the current that's generated transfers into heat. That's called Joule heating, and Joule heating occurs in all electrophoretic processes. It's something that limits almost all electrophoretic processes in how readily they can be scaled up, or how far they can be scaled up. If you get too hot, the electrolyte solution can boil, and if it boils, it creates a bubble in the solution, and the ion mobility stops and the circuit shuts down. Okay, so you have to provide cooling to electrophoretic processes that limits the scale that you can run electrophoretic processes. So it's something we always have to worry about if we're doing electrophoretic separations. I don't dwell on it here. We dwell on it a lot in the book. And then there's that pesky reaction rate. Okay, so we have to account for the exchange between the charged ion and the uncharged ion. It can be either plus or minus, and in some cases you have both that are occurring. So that rate, as I mentioned, is almost instantaneous compared to the rate of movement of the ions. And that creates a stiff differential equation that is almost impossible to integrate when we start to put that together. There's another constraint, and that other constraint is local electroneutrality. So we always have to have the number of positive charges in a small volume, or a local volume, have to equal the number of negative charges in that volume. That always occurs if you have an aqueous solution. The pH of that solution will change as ions move through the solution, because something like a sodium ion that cannot equilibrate, a sodium ion will displace and push protons to form neutral water. Okay, a chloride ion will force hydroxyl ions to combine with protons to produce water, so that we maintain electroneutrality everywhere in the system. And that adds another constraint on these reaction rates, is at the end of the day, these reactions all equilibrate to comply with the electroneutrality constraint. So it's a very difficult system to actually integrate and to solve. Okay, this rigorous model is not particularly useful because of that. It presents a stiff integration problem. This has been covered by Dudley Seville at Princeton and his co-workers in 2 articles. They talk about how you do this and the limitations of their numerical integration. Since the electrolyte in the electrophoretic channel is not moving, there's a more practical model that can address this, and this has been outlined by Juan Santiago and his group at Stanford, and they've developed an open source simulation tool for various processes in electrophoretic separations. Now let's talk a little bit about a more practical way to approach electrophoretic models. Let's think a little bit about the electrophoretic mobility. Okay, the electrophoretic mobility is the molar rate of transport, in other words, that flux through a given area, divided by the concentration, the charge, and the field strength. Okay, dV dx is the electric field strength. It's the voltage drop per unit length. Okay, and that has units of length squared per unit time. That sounds a little like diffusivity. That's why electrophoretic mobility is related to diffusivity, but it's per volt. That's the added piece that makes electrophoretic mobility differ from diffusivity. Okay, so, but what is Q over concentration? Well, it's moles per length squared per unit time, that's Q, and concentration is moles per length cubed. So if we look at the units on this, that's really velocity. So Q over concentration is velocity. The lower the concentration, the lower for the same flux, the lower the velocity. Okay, so that means we can actually measure something. That's velocity. We can measure how fast an ion moves through the solution, and we do that in electrophoretic separations. Believe it or not, you can measure how long and it takes an ion to move from a starting position to a final resting position. As long as you can see or identify the ion, you do it as a bolus at one end, you pick it up as a bolus at the other end, and that gives you an idea of the velocity. If it traverses a distance L over a given time, that's the velocity. So it's a measurable quantity. And if we know the field strength, we can translate that into the electrophoretic mobility. Once we know the electrophoretic mobility for a given charge, on that ion, we can always calculate the velocity from the electrophoretic mobility times the charge times the field strength. So this becomes the most important equation in this alternative practical model for electrophoresis. Now there's one other thing we have to digress into, and it turns out we typically use glass or silica as our flow channels. We can also use plastics. The same behavior works for all plastics, including Teflon. But the surfaces of that glass wall are or can be ionized. If we have silica, that's glass is mostly silica. If we have silica, we're going to have pendant hydroxyl groups along the wall. Those hydroxyl groups have a pKa of about 3.2. They will donate a proton to the aqueous solution. And that means at any pH above about 3, there's going to be a net negative charge on the wall. Now, the same thing is true for polymethyl methacrylate, for Teflon, for all these things. They all tend to generate a zeta potential at the surface, which is negative. And because of electroneutrality, that attracts ions from the solution to the wall. So we get a layer of sodium ions against the wall. In this case, I've shown it as sodium ions. It could be any positively charged ion. And that introduces some issues in electrophoresis where things that are charged can sometimes be attracted to the walls, and that can actually add a chromatography component to the solution. So it's always something, there's little complexities here that sometimes you have to deal with. But in this case, let's keep it simple. We'll say there's a lot of sodium around in the solution, and that will form a layer, the Debye layer, adjacent to that wall, which is net negatively charged. Now, what do you think happened? Now, the wall is fixed. The charges on the wall are fixed. They're part of the silica matrix of the glass. But the charges adjacent to that wall in solution are not fixed. So what happens when we slap an electric field across this? Well, we put an electric field across this, and those positively charged ions that are just floating around near the wall, as a Debye layer, they say, "Oh, I see a field strength. Yahoo, I'm going to start running." And to the solution inside that capillary, it now suddenly looks like the walls are moving. And the neutral solution inside starts moving with it. Remember the velocity at the wall is always 0. Well, the solution thinks that sodium ion layer near the wall is the wall. Well, if it's moving, it's going to have a velocity at the wall of 0, there's nothing inside that capillary, if this is just a pure zone electrophoresis type of experiment, there's nothing inside that capillary to slow it down. So the velocity at the wall will propagate in, and the entire contents of that capillary will start moving towards the anode. So it looks like the walls are moving with nothing to hold it back, and this is why we typically add some sort of gel matrix into the electrophoretic channel. For those of you who have done these kinds of separations, gel electrophoretic separations, the reason for adding that gel is it actually provides or one of the reasons I should say that for adding that gel is it provides a matrix that inhibits the movement of the electrolyte when the Debye layer starts moving. Okay, it's really a cool process to do that. But the fluid goes along for the ride. Now, the rate at which those ions are moving depends on the field strength. So we can define an electrophoretic mobility for the EOF. Okay, so it's no longer a electrophoretic mobility, it's really an EOF mobility, or an electroosmotic flow. That's what this is called, is electroosmotic flow. Now, as long as the capillary or the flow channel or electrolytic channel is uniform, we get a very nice square wave movement. Okay, however, if there's variations in the charge on the surface, we can actually get superimposed Poiseuille flow with EOF flow. Okay, and that's a challenge because we end up seeing the walls will move faster. They're up to a point. They build up some pressure, and the back pressure will cause the contents to start pushing back and forming that bullet-shaped thing that we saw in the capillary chromatography lecture. Okay, this ends up causing a mixing inside the flow channel, which completely destroys your separation. Now, Her et al. And Juan Santiago's group actually measured this, and they showed this by making microfluidic channels and then measuring or putting a coating on those channels to try to suppress the electroosmotic flow. There's a number of coatings available in the literature for doing this. I used to manufacture one of those coatings, if we look at this, there we go, you can see where most of the flow channel is EOF suppressing. We get EO driven flow. This is a neutral fluorescent marker, and you can see how it migrates down the channel in a fraction of a second. These are in milliseconds. But the same channel where only 10% of it was coated and the rest was not coated, you can see the superimposition of EOF flow at the walls with pressure-driven flow to produce that bullet-shaped Poiseuille flow in the center. And that destroys your separation. So this is when you start using coatings to alter the EOF, you have to worry about the uniformity of those coatings. There are some good ones out there. The Eotrol and Ultratrol line are the ones that I used to manufacture, and I believe those are still, well, as of this point, those were still available. All right. Now, EOF can work for or against you, and it's a little counterintuitive, but if we think about it, the actual apparent mobility of a given ion, that's mu apparent. Mu apparent is equal to the natural electrophoretic mobility plus the electroosmotic flow mobility, the equivalent electroosmotic flow mobility. So we can combine those two to create an apparent mobility. And that's really dependent on the velocities of the two. And so now we can get the velocity of an ion. Once we know what the EOF is, or the EOF mobility is, and we know the electrophoretic mobility, we can calculate the apparent velocity of that molecule. And if we divide the length of the flow channel, or the distance down the flow channel d, by the velocity of the ion, we can get the time it will take to reach the end of the flow channel. Now, conceptually, let's think about this in very simple terms. We have a river, and we have a starting point, and 100 meters downstream we have an ending point. And swimmer goes into the river, okay, and he starts trying to swim upriver. But the swimmer can only go a meter per second. The river is flowing at 2 meters per second. Okay, so the net, the apparent velocity of that swimmer, that ion, the apparent velocity of that swimmer is 1 meter per second downstream. So he's going in the positive direction 1 meter per second. It will take him 100 seconds to go 100 meters. The river wins. It pushes him out. Now, let's compare that to a swimmer that's actually moving downstream at 1 meters per second. So in one case we would have a negatively charged ion, the other case a positively charged ion. Think of it that way, if the upstream is the cathode and the downstream is the anode. So if we have another ion that's net positively charged, he's swimming with the current. His apparent velocity is 3 meters per second, so he will reach the downstream point in 33 seconds. So he will separate from the other swimmer, even though both of them will continue to move down the flow channel. Okay, the river pushes them both to the end, but because their relative charges are different, the direction in which they're moving is different, one will get there faster than the other. Okay, the downside is with EOF is, what if we have a really good swimmer and he's swimming upstream at negative 2 meters per second. Okay, the river's moving at 2 meters per second. He'll never reach, his apparent velocity is 0, he'll never reach either the starting point or the ending point. He's stuck in that river forever. He can't go in either direction. He's exactly counterbalancing the river. He'll never come out. So that's kind of a way I like to think about it. You think of the starting point as the cathode, the ending point as the anode, and the charge for electrophoresis, if it's moving towards the anode, it's positive. If the ion is moving towards the anode, it has to be positively charged. Okay, so that's one way to think about the charges and where they migrate. If it's going towards the cathode, it's negatively charged. And it is possible to reverse the EOF with certain coatings so that it moves from anode to cathode. But the natural movement is from cathode to anode in almost every type of electrophoretic flow channel that you can create. All right. Now, separation is fairly simple. It's the width of the peak that we're using. Now, remember, there's no the ions are the only thing moving. So if there's a pH gradient generated in the column, you might be able to get some ions moving faster than others at different times, depending on their fractional charge. But effectively, all ions, because the equilibration is so quick, all ions are moving at a uniform speed. So whatever the peak width is for the bolus that we add at the beginning of the flow channel, that's going to be roughly the peak width at the end, minus a little axial dispersion. So it'll be a little bit wider. So as long as that peak width is smaller than the difference between when the two components come out, then we've attained separation. And we can relate that back to the apparent mobilities of those two components times as a function of distance and field strength and the initial peak width that we put in. So This is how we get separation in zone electrophoresis. It's by assuming things will get there at a certain point based on their parent velocities. All right, so that's the two ways to model electrophoresis. There's a very robust way to do it that's almost impossible to integrate or to work with. So we tend to do it through electrophoretic velocities, and we've shown how we can adapt to the Debye layer and the zeta potential of the wall, and which generates a electroosmotic flow. But this is the inherent model of all electrophoretic processes. But there's a lot of different varieties of electrophoretic processes. We're not going to discuss those here, but they are discussed in great detail in Chapter 11. Again, I encourage you to buy the book. BioSeparationstext.com is where you can find links to purchase the book, and you'll find resources that'll help you with a lot of the calculations, particularly in scale up or in physical properties of molecules. Okay, and with that, I thank you.